Well, I hope everyone slept well and is well rested. We're going to have a full day today with a lot of material, so I'm going to try to go over, well, as much as I can. But anyway, all the slides are going to be available for you in case you want a little bit more of details. And again, as I said yesterday, I don't mind if you interrupt me for questions in the middle, right? Because that makes actually, that interaction is very good for everyone, because somebody can be asking the same questions as you do. So I don't mind to stop briefly and just, explain and then continue. So if you feel or, any questions right in the middle. Good morning to also all of the online attendees. And we're going to be the last kind of fundamental on water flow. Yesterday we saw the determination of the unsaturated hydraulic conductivity function. And I hope I think it is not a difficult thing to do. Now you know that there are estimations for that, if you can measure that or you don't have the time or the money, but also you can do stuff in the laboratory or in the field that can be, well, this for the research side is important. Today we're going to see the water flow through unsaturated soil. I'm going to get a little bit more into the steady state and transient conditions. And I have for you a couple of examples that we run in Fluxes for you to know, to understand how all these theories apply to practice, right? So you're going to be learning about water flow, steady state and transient water flow. I briefly touched yesterday on that. And a couple of examples, one for an air dam, which is a classic sea pitch analysis, and the other one for flooding under pavement systems, that also you can just model on that, at least to figure out how these will impact your stiffness and how that will impact your design procedure. That's the important part, right? How you applied all this information to your practical engineering problems. So partial differential equations, I'm not going to go in detail. I'm not going to go step by step in here. I assume most of you have done that into your classes, math classes and graduate classes. But at least I'm going to show you what is the equations that we solve and we have solutions for and how to apply that. So like I explained yesterday, the sea pitch can be either steady state or transient, right? Both of them, the steady state, you're going to need the hydraulic head, we explained a lot on that one, and the coefficient of permeability or hydraulic conductivity, and they're kept constant during the whole process. For the unsteady state condition or transient conditions, we do the hydraulic head and the coefficient of permeability change with time. That's what is called transient, it's just time, right? And the hydraulic head changes with the boundary conditions with respect to time. What that means is that if you have any problem, when you do have environmental conditions changing continuously, you're going to have always a transient flow condition in your problem, okay? So the examples are many. Infiltration through air dams is the classic example that you need to learn. Evaporation through unsaturated soils for those working on evaporation. Groundwater contaminant control also. Everything that moves, the water with time. And the water flow under pavement structures after a flooding condition, that a special case that I bring to this audience today. So how the hydraulic conductivity vary with the space, right? This is important because I find out that the main cause of inaccuracies when you model sea pitch analysis is the wrong value for these unsaturated hydraulic conductivities. We usually assume things, right? Assume things. So this is something that you really need to be careful when you are running any one of these analyses. For a steady state sea pitch through saturated soils, the case that you all know, the permeability is a constant with respect to time at each point in the soil. This is what we assume, okay? Why? Because we do have a condition, it's already saturated, right? So the fluid flow through flow, the fluid flows through the fluid, right? And if it is 100% saturated, then you're going to have kind of the same permeability going on, okay? However, the coefficient of permeability for unsaturated soils change from one point to the next, right? For all that Professor Barar explained you today, 2 days ago, about all these different capillaries that you find full with water or not full with water, okay? Well, now the spatial variability usually in saturated soils, if we have any variability, is attributed to the heterogeneity of the soil, right? We got a little bit of heterogeneity, then we said, okay, that can vary a little bit. But for unsaturated soils, the permeability is not because of the heterogeneity, mostly, is because of the changes in moisture content or matrix oxygen, okay? So again, 3 examples in here of how permeability can change in an unsaturated soils. I guess we can, I like to put it in groups so, we can find the information easily when you need to get to it. So one soil, for example, you can have a soil that is heterogeneous but isotropic. That means, for example, that you do have in here, this one doesn't work in here. No. You got 2 points A and B. I hope you guys can see that well. For point A, the magnitude of the permeability is different from point B, right? So that's a high heterogeneous situation. The isotropy means that the permeability at that particular point on the horizontal and vertical direction is the same, right? So this is the isotropy condition. So you can have that condition. You can have heterogeneous, but an isotropic condition, which you do have the permeability changes with respect to space, but at that particular point, the horizontal and the vertical are different. But you can have the case that the two of them, the ratio between them is the same, right? It actually, it gets to the modeling is a little bit much faster if you assume that. Or you can have a continuous variation in the permeability with a space in which not only there are difference in the conditions of the soil because of spatial variability, but also the ratio between those two are going to be different. So spatial heterogeneity is the general case that we use for unsaturated soils, okay? And that's why the time consuming when we run those kind of problems, right? I mean, I'm talking about time consuming, probably will take you a couple of more hours, right? But for the design is much better, and the design, that structure that you're building is gonna last 30 years, right? 40 years. So we need to be patient and being able to run all these problems. All right, so like I said, those are the 3 conditions I just explained. I just have it in here written for you so you can read your notes later on. Okay, so how we model that flow. If we just start with the typical one-dimensional flow that actually for us geotechnical engineers is the most common, because we're looking at very extended situations and our problem basically is a vertical problem. The water flow under a steady state condition that can be generated either by infiltration or evaporation, okay? So what I have in here is that usually when you have a steady state condition and you run a steady state condition problem for those, how many of you model all the time or do some modeling? I saw 1, 2, 3, 4, 5, 6, okay? So when you do that and you do, okay, I want a steady state condition, okay? You can just say basically at the top, we're not gonna do any infiltration or evaporation. We're just going to figure out where the water table is, all right? And basically it's gonna create a static equilibrium with the water table that is equal to gamma times the height, right? So it's a line that is a negative pore water pressure, right? We assume that the pore water pressure, the suction is, oops. Here we go first. I guess this one is fine. We assume that the pore air, again, so just keeping that in mind, is equal to your suction, right? So I'm talking about that the line that we saw in there, okay, here we go. the line that you saw in here is the negative pore water pressure, right? So if you assume that the pore air pressure in here is atmospheric, you can assume that to be 0. That's basically your suction value, right? Going up is your steady state equilibrium condition. Now, if that is the case, and if you have a negative pore water pressure at equilibrium with the groundwater table, this doesn't vary with time. Actually, that's the one that you have all the way when you run a steady state condition, right? So this one is, but what happens is, usually we do have all this influx or outflux, evaporation and infiltration at the top. And therefore, this line in here starts deviating. Whether you do have a steady state evaporation, your line is going to be twisted to this direction, all right? You're going to have more evaporation, so you're going to have higher negative pore water pressure. When you do have a steady state infiltration, you're going to have more water in here, and the line is going to twist from this direction, okay, until you get a steady state condition. If you run one of those steady state conditions when you have an infiltration, which is kind of a constant, every day, right? Or always is this one, you're going to have a steady state flow downward condition, and it's going to be running like that, okay? So this is important for us to understand, and this is what I wrote for this one. So now with this graph in mind, the three different water flow conditions can happen through the unsaturated soil. One is the static equilibrium, one is the steady state flow when it is downward, and a steady state flow when it's upward. Okay, so this is the pore water pressure, but also you have the gravitational head distribution, right? So you have those two heads in there, and this is the other head. This is the gravitational head that you do have due to the overburden pressure and, to basically the height, right? That's the second head. And we just assume usually that the velocity head is nil. All right, so those two can be used to compute the hydraulic head profiles generated in the soil to different boundary conditions that you're going to have in the field. Okay, so these line to lines, as I said, can be explained, the water flow rate in the magnitude and the direction through the unsaturated soils. For that, we did continuum soil mechanics, and the continuity equation under the steady state condition. You're always going to have that for any element of soil, the mass of water flowing in has to be equal to the mass of water flowing out, right? This is your continuity equation that must apply always for our condition on this one. And basically, you do have the Q in minus Q out equal to 0. And the Q in minus Q out basically is your Darcy's law, right? It's just equation in which you do have the flow of the water for, I'm going to give you the Darcy's equation in a minute. This is just Q in minus Q out equals 0. And then because, you can't just get this one out, and basically you can have a net flow through the element that can be written as this one, and this is just solving this simple math, and then you get the Darcy's law into that equation, right? And this is the flow rate, which is the permeability as a function of suction multiplied by the hydraulic head, and then you got the equation that yields that, right? This is the equation that can be used to estimate the hydraulic head profile for that. So we can write partial differential equations for that. In this case, well, because you do have one, and this one is also a function of that. So basically, we do have the change in water coefficient of permeability, K, in the y direction due to changes in suction. And this is the equation that can be written as a partial differential equation. And I'm not going to go through that, step by step. But I'm going to tell you the different conditions or the different cases that you're going to have. Let's say, for example, a saturated case. So this is the general equation, but you have an unsaturated or heterogeneous condition. For a saturated condition, that permeability becomes a constant, right? It's K sat. Oops. That Ksat right here, right? And basically, this one also becomes a constant, and this is your Ksat. And we leave it like that because it's heterogeneous. For saturated and have homogeneous condition, we don't have a change in the permeability with respect to Y or a function of the hydraulic head. And therefore, that only applies to this cause, and this K, which is a constant, gets away from that, okay? So that's the second case of the equation. Now, this is just state condition. That's the steady-state condition, the partial differential equation you're going to find. The second one is the transient CP condition, all right? When that happens, we now need to take into account not only the permeability function as a function of suction, but also we need to figure out what is the storage capacity of your soil, all right? Because you're going to be working that with time. And that's when the saltwater characteristic curve comes into play again. Many situations are encountered for that, where the ground surface is pretty much a moisture flux condition. You're going to have a transient flow. Everything that it changes in one of the boundary conditions, that is make the flow all the times to be continuously changing with time. So we got, for example, boundary conditions in here that are rainfall, for example, right? So you can put rainfall in one side, you can have no flow of water conditions on some other side, you can put water table in here or just a water table in between and no flow conditions, or you can put a total head, for example, okay? Like, for example, if you put in here a water table, in here you can put that this one is your suction equals 0 line, right? Suction equals 0 means saturated. And then you can run the program with this one to be fixed, right? If you want the groundwater table to fluctuate, then you need to use another condition. All right, so you set up your program and you set up the first very carefully what the boundary conditions you need to work with, all right? Whether there is no flow here or a constant head condition, or if there is some influx or evaporation going on, okay? So those are the conditions that you're going to be allowed to do for every one on those models, right? And basically, the nice thing is about when you have the cover with the environment, this thermal boundary condition that you have in there can be an actual evaporation flux, right? And it's very interesting for us. So that means that, for example, you do have a actual potential evaporation for a particular site, right? And all these numbers we know based on the weather station conditions, okay? Now what we need to figure out is the actual evaporation that the soil is going to try to, get the water out. Guess what? Remember what the saltwater characteristic curve means, the soil moisture retention, right? So that, the soil is going to hold some water. And even if you do have this actual evaporation, the potential evaporation, you're going to have only some actual evaporation going on, right? So this becomes a flux condition, very interesting for, I guess, a couple of you are working on evaporative things here. I didn't bring that example. So let's go for example, an air dam. And we're going to go a little bit more on the running fluxes on this one. But for example, during the filling process, so you make an air dam, you got, and I didn't put a coin here, just a simple air dam that has a filling process. It's going to be a transient flow, right? Because it's going to be varying with time, right? You're going to have to fill that reservoir on this side of the road. So you can go from here all the way to there, and basically it's a transient flow as the reservoir is filled. Once the reservoir is totally filled and you leave that level alone, you just don't change it, that becomes a steady state condition for the soil once it equilibrates. Okay, those are the two. So this is true if the water level is kept constant, and a small fluctuation can cause any infiltration of evaporation that it becomes transient in that point. Probably we don't do that all the time. We just do a steady state condition for the flow. But if we do have some situations, that the example I'm going to show, that we're going to be changing that reservoir level, okay? And that's important for that. All flows are heavily influenced by the conditions that you have in the unsaturated soil, and you need to consider the anisotropic permeabilities. Like I said, is important. Both directions that you characterize the material very well on that, you know, is important. Is the first parameter that you need very well characterized, okay? And that's when you're going to tell your boss that I need money for this, right? Because, you know, we cannot, you know, sell short this kind of analysis. We need good data. Otherwise, you're going to get garbage, okay? No matter what models we're going to have. We need the equations that are derived based on these conditions, and the water flow properties are defined by the greatest and the least coefficients of permeability. Usually when you do have a very big project, you go ahead and check different places, right? You cannot run every single place. You cannot just change every single place. So we usually are conservative and we do the maximum and the minimum that you can get, right? And then you work with those kind of values right there. Usually in here is a two-dimensional flow analysis. We neglect the Z direction, okay? Again, anisotropic means that the permeability depends on the position within the soil, okay? Matrix suction will vary with soil mass, and therefore the permeability will vary. We analyze the steady state condition by continuity of the water phase, and that the ported pressure is assumed to remain constant with time, okay? Ported pressure, usually you don't change it, unless you're putting some suction in there that I don't know how you're going to get that. To model anisotropy, find the ratio between the largest and the least permeability values that usually give you a good value, or you know what, unless the one that is more predominant in your problem. Use the same ratio for any point within the soil profile, and you know you can do the heterogeneity, but you can simplify the program by just doing one ratio. For transient flow analysis, those are the partial differential equations you're going to need to deal with, or the program that you're going to be using or programming need to do. And this is the change in the permeability in one direction, and this is the change in permeability on the other direction. And this one is going to be the storage capacity right there. The M value, I'm going to show you in a minute what it is. And basically, this is the change in the hydraulic head with respect to space, and this is the change in hydraulic head with respect to time, right? That's your partial differential equation right there. And those values are function of the matrix suction, as you already know. And this value is what we call the water storage modulus, or water storage capacity. For isotropic conditions, you're going to have that this value and this relationship, because it's a function, and these ones are the same, right? It's isotropic, and therefore you can use the same value right here and right here. And we still need the permeability function as a function of suction plus the saltwater characteristic curve. M value here, this is your saltwater characteristic curve. Usually, if you take the derivative of the slope of the curve, you're going to have the water storage of that, okay, for every one of the points. So which one do you take? Which one do you take? We usually take, for the problems, kind of a point right here in the middle for that, okay? We don't do the whole function analysis. We just take the water storage for that. But this is the value that you can take. Okay, so now this is all you need to run C-pitch analysis. You actually need those two hydraulic properties or function, the saltwater characteristic curve and the K and SAT function, okay, as a function of suction. Okay. Any questions so far? This very, very compacted material, right? It's not. Okay, everybody understood. Good. So a couple of examples in here that we run just to demonstrate how important this one might be in the practical application, right? And it's okay if we find that the difference are not much. I think when we run it is when we need to realize that if including all these parameters makes sense to you economically, it's okay. If you find out that it's not, fine, just run a saturated analysis with no problem, right? But I think it's important that you understand that some of the situations you may save some millions of dollars in here if you just basically do it right, okay, that way. Do it right means a little bit more realistic analysis. So what is the impact of water level changes on earth dam? This is a transient flow analysis, right? And usually when these water levels are pretty quick, and that happens when you have to, for example, to draw down a reservoir, okay? There is a danger, there is an earthquake happening, you don't want this water at this level, you want to lower that. There is a lot of a lot of rainfall, and this, is at capacity, so you want to lower that. There are many situations when you have the air dams have to be lowered down, okay? And usually you want to do it at a rate that is not dangerous for the excess pore water pressure to occur, right? So this is the typical case of a transient flow condition, right? And why it's important is because you can cause instability on this embankment or this side of this if you do it too quickly. So for that, we need to consider what is the pore water pressure monitoring inside. And sometimes we do have all these sensors in there, and we can figure out how much excess pore water pressure we got, and make the calculation of total stress minus pore water pressure, and figure out where your effective stress or excess pore water pressure is, and all of that. However, you will like some modeling as well on this one. For that, you're going to need a couple effects of the water level change and the stress field, and the water level change and the dam stability. So you have to have CP plus instability, shear strength analysis, factor of safety, right? So you're going to need that. This situation requires unsaturated C. So it's good to know where the CP and when the water is going. But you want to figure out also that this one is stable as that occurs, okay? So we run a little example in here when the level is defined. First of all, the long-term condition, steady state condition, when the water level reservoir is at 25 meters. And two conditions when we need to do the drawdown. One, rapid drawdown, like you have to go from 25 to 5 meters pretty quickly, or a slow drawdown, and figure out how this will affect the factor of safety of your dam, right? This is right there in the practical application. So we can do any assumptions in the program. The more you have run this before, then the more you're going to be understanding what kind of assumptions are going to be working or not. Usually I do it, I put the assumption and I don't put it, I run it, I figure out what the difference is. So, you need to play with that, because you need to take decisions, probably what assumptions you need to make for running those problems, okay? So I neglect thermal CP analysis, so I don't have, that couple analysis. Interfaces, properties of the dam. Only consider dam, soil material parameters, and the groundwater table properties. Time-dependent effect on the hydraulic and transient flow condition. Isotropic condition, in this case we didn't vary the heterogeneity, but you know that we can put that in there, right? It's just to run a little bit faster. And assume the initial phase to be a steady state, and then by gravitational loading, and then we make a full couple flow deformation analysis for the transient drawdown, all right? So you create your geometry. For those of you, if you haven't done it, you will do it, okay? You're gonna do it either here or when you graduate and start working. See, this is the subsoil material, and we have that field. We got some core materials in here, which is usually the impermeable side, and basically you create this one is kind of an AutoCAD kind of similar stuff to do that. The dam height, put 30 meters right there, and the top and bottom widths 5 meters in here and 185 meters down here. Geometry, and when the parameters you need to start getting. So we use Moore Coulomb for the shear strength criteria. You can use any other parameters or constitutive models that you have available. on the program has available. And we got for the coal, the properties for the core, for the field, for the subsoil. So what properties do you need? You need the unit weight, right? The gamma wet, gamma saturated below the groundwater table, gamma wet above the groundwater table. That's very important. And for the strength run, you're going to need the modulus, Poisson's ratio, cohesion and friction angle. These are the typical shear strength parameters you're going to need for that. And for the groundwater flow or the seepage analysis, we use the Van Genogten equation, to fit that one. And obviously, it uses Darcy's law or a modified Richards equation. Horizontal permeability, vertical permeability, the saturated value, we put them, this is the saturated, we pull them to be constant, right? Isotropic conditions. And then we tell the guy, just use the Van Genogten estimated equation that you saw yesterday to calculate the whole function, okay? And we give them a soil water characteristic curve data for all the soils in there, because you're gonna need that. So, three analyses were run. The first one we call high flow constant case. Reservoir level was kept at constant level at 25. Then a quick drawdown when we watered the level down from 25 to 5 meters in 4 days. And the other one, a slow drawdown when we did that in 40 days, right? In 40 days. We got more time and we can do that. Assumptions, the water elevation drop was kind of a constant or linear as a function of time, okay? But you can do any assumptions that you believe is necessary. With that, we run the program, and then what you get is pore pressure distribution, right? Pore pressure distribution, whether they are positive or negative, right? If it's positive, is the one that you've been always using. The negative are your suction values, right? Your suction values. High pore water pressure that were generated. You can see the high flow analysis in here. It doesn't look good to me. So what we got in the left corner, okay, near the left corner of the soil, when the flow water was kept constant, you can see higher pore water pressure develop on this one. As you go down, right, on the slope, then you're going to have more pore water pressure because you got water under the, groundwater table. And then you get to a point when you do have all, high pore water pressures all the way down. So you increase with that. Now, when you do have a quick drawdown, we can see that the pore water pressures were higher than the ones in here, okay? The pore water pressures were high. But we found out that to be kind of the same. But wait, the problem is not the pore water pressure, it's the excess pore water pressure that you are putting together on that. And then we just figured out what the excess pore water pressure were. And that's when you see the big difference. This is the one that's going to cause the problem for you. It's going to be the excess pore water pressure, right? And you can see when you have a quick drawdown, the excess pore water pressure in here are going to be much higher. That means the excess pore water pressure means that the soil is going to have to drain out, right? To drain out at a certain rate. It's consolidation theory, right? At a certain rate to get to the pore water pressure that you saw on the slide before, okay? And this one will have less pore water pressure in here build up than the less pore water pressure than the high quick drawdown right there. All right, so with this information available, we went and checked for the factor of safety. What happens with the factor of safety once you have these conditions, right? So we use a point on the top level corner of the dam, and we just run a slope stability analysis for that. You can use any methods. There are many computer programs that have the method of slices, this Morgenstern, everything, just one wedge, everything like, you need to do for that particular soil, right? You can run that. And then we plot the factor of safety as a function of the deformation, and we can see here that the factor of safety is about 1.2 when you do have the steady state condition. When you have the slow drawdown, your factor of safety goes down. There are some excess pore water pressure to about 1.6. And when you have the rapid drawdown, you got a factor of safety about 1.2, all right? So now with this information, you can make decisions how much time you're gonna need to do the drawdown, okay? So how much you wanna risk. It all depends on the amount of time you have, the amount of money that represents, and therefore now you have some information in there to do a safe and a good engineering analysis for what you wanna do, right? There is never a right or wrong answer. There are answers for you to take decisions. That's what it is, all right? This is example number 2. This is the impact of unsaturated flow under the flowing conditions on subgrade stiffness. And basically, this one also has a lot of assumptions in there, but I thought it was a very nice thing that, what we can use probably to analyze. So here is the problem. The highways or the roads in the United States are managed by the State Department of Transportation. We got 50 states, we got 50 state departments of transportation. So we make, and this is a whole full lecture, I made a survey of what if they have an implementation plan in case there is a flooding event. And they all do have kind of an emergency response to that, right? But the problem is, they don't know when to open the road again after a flooding condition. They just wait to the water to subside or run off. Then they go to big machinery over there to take all the debris out. And guess what? If there is not enough time for the water flow to get out of it, they're damaging the road with the big equipment they're putting there to get the debris out. Okay? So the flooding is not causing the big problem, it's their own equipment at the wrong time, right? Obviously, they want to open the road because, there are thousands of people trying to get from point A to point B, right? And, the infrastructure is, so we need that. So we need to figure out what is the steepness, what is the soil conditions after a flooding, problem number one. Problem number 2 is to figure out how much time do you need to open this road. Very 2 practical applications and questions that you're gonna need to sit down and help answering to the government, okay? So the flooding, obviously, you got a lot of water in there and then the water starts infiltrating the soil. If everything is paved and everything, they will find a way, the water will find a way into your soil, okay? Hopefully you're gonna have a good drainage. That's another point that we need to check, right? Have good drainage, but the water is gonna get, we do have over there, the roads are always have shoulders that have opened to the environment, okay? So we get the water from the sides. We got cracks on the pavement, so we got also water through cracks, okay? There are many ways to get water into this, into the subgrade of the materials, okay? And the worst thing is that will reduce the pavement stiffness, right? And the strength characteristics, although I'm gonna talk about stiffness because I think this is more fundamental to characterize the subgrade material on that, okay? Subgrade might get saturated, might not get saturated, we don't know, but the roads are unsafe. And not only that, you can damage if you put a big truck going out through that road if the soil has, the steepness goes down tremendously. So our objective, this is just part of a project that we are finalizing and is getting very nice results. It was to develop a science-based or a mechanistic-based framework to assess what was the steepness loss or the resilient modulus reduction, but also the recovery time after the flooding, to see how much time do you need to open the road. Now, if I can tell you that it takes 1 year to recover, 20% of the, it's your problem and it's your decision to know where to open the road, right? So with those 2 information, we can figure out with the time after the flooding when this Department of Transportation of agency can open the road. Okay, so we make assumptions and well, we create a big profile here because we got groundwater tables down there because we wanted to figure out for unsaturated soil conditions, right? But obviously we can put the groundwater table higher. We put it at 3 meters, at 6 meters. This is very, well, when I leave, the water table is 30 meters down, 30 or 40 meters. So this is pretty shallow, actually. In here, you're going to have water tables. So we got an asphalt layer. We got a granular base material. Are you guys familiar with the AASHTO classification A1A? Okay, AASHTO classification A1A is pretty much a well-graded, well-graded gravel, something like that. There are some pavement engineers in here, better than, I have some in that. So I got an A1A soil for the base, and I get an A3 soil for the subbase. An A3 soil is a poorly graded sandy material in there, which is very good for subbase materials. And what I did is we buried the subgrade material. We put it as a very permeable soil, A1A, like a sandy gravel material, all the way to an A76 soil, which is a high clay material, right? So we vary the soil from gravel, sand, silt, and clay, all right? And we also vary the groundwater table, and we figured out boundary conditions. And the first thing we did was to, okay, before the flooding occur, you are expecting that the water below your covered area has tended towards an equilibrium condition, right? It's tending always. You always get infiltration, you get evaporation from the sides, from the environment that you have the roads, but there is always a tendency of that road to go through an equilibrium condition, right? Okay, so we assume that if we run a steady state condition, it will be a nice place to start. Okay, we can start from any place that you feel is important, right? Like, for example, if you know that there's been a whole week before that with a lot of rain, right? So you can probably run this one and have a profile of suction, not the steady state condition with the groundwater table, but, lean towards any infiltration or evaporation, right? And you can start with this one. So we started from a steady state condition for the sake of showing that to you. We neglect thermal gradients, the boundary conditions, the groundwater table will remain constant, so we put a constant suction value of 0 right there. Lateral conditions, no flow, so anisotropic conditions just to run it faster, K vertical and K horizontal the same. Then we run the steady state groundwater flow condition, and then we got a transient analysis with the weather conditions. We put a lot of flood, and actually we simulated what happened in New Orleans, I don't know, 2004 or something like that, that it was the Katrina hurricane, and we knew how much infiltration, how much water went through that, and then we just start getting, I'm going to show you that in a minute. So again, we run the material properties. We have a 4-layer system in here, and we got the subgrade material properties for every one of the soils. For the granular beds, this is an example for the asphalt concrete. Again, these are embankments of the road and also slopes. Alrighty, so again, the slopes of this pavement on the sides, those are embankments. It's called road embankments, right? And every time you need to design for a road, and you're going to see that a lot in the afternoon, how we can just use the material stiffness that is needed for the design of the road, but also you need to design for the stability of those embankments. Okay, you have to put the right slope in there, and you have to run some slope stability to figure out what's going on in there, right? So we ran also a couple analyses with the deformations analysis and the groundwater model. Why we did that? Because we wanted to see what happened with the flooding, but we didn't want to fail the slope before knowing what happened with the flooding through different soils, right? So in this case, we put a factor of safety equal to 1.5. And it said, no matter what happens, just keep the factor of safety of this road at 1.5, okay? So we organized those conditions, we designed for that, and then we were able to, so the maximum condition for water will not fail the embankments for slope stability, okay? Because I want to see the fluid flow happening there. But obviously, you can run those programs by telling them, okay, I want to figure out what is the slope stability of this thing, and see what it fails or not. So We ran more Coulomb for that. We ran the groundwater model for that using Van Ogden parameters again, Darcy's law, and these are the parameters for Van Ogden. Saturated, I should say saturated here, hydraulic conductivity for different materials and so forth. These are the saltwater characteristic curves we use. We just get some data points for A1A, A3 salt, for all of the salts. We run like 6 or 7 soils, and we just put the Van Ogden feed through that one to figure out the parameters. And based on this SWCC plus the saturated hydraulic conductivity, the program will use the estimated Van Ogden equation, so we don't do instantaneous profile testing, and they will create the two functions. So we got the SWCC and the K and SAT function for that. Okay, these are just, I just put in here the values that we use for that and the Van Ogden parameters. If you want to run a little bit of solver, okay, how to obtain A, N, and M with the Van Ogden equation. And these are the actual, the square error that you get. This is usually, you got the actual value, you got the predicted value, and you try to minimize the sum of the square errors for that, right? This is by what? By changing these parameters. Changing these parameters until you get that sum of the square errors minimized, right? And then you get the best fit to your data. I will argue to my student that this is not the best fit, but he will argue something. The data that we went through very low here, Van Ogden usually flattens down before. I told you that yesterday. So basically, it's very difficult to get Van Ogden to all the points on the high value, but it's okay for that. Okay. So these are the climatic conditions we impose. You can also impose any climatic conditions. We use 4 different places. Louisiana, when the rainfall and the climate is like your climate here, is very wet, humid, and the infiltration potential is much higher than the potential evaporation, all right? Florida, which is a little bit less, but still humid. Texas, which is kind of in the middle, start getting into the semi-humid, semi-arid regions. And then Arizona, when we live, when it's very arid, like with the evaporation, is much higher than the infiltration on a yearly basis. And for the first day, after we ran the steady state condition, we said, okay, now we run the transient condition. And we did is for the day number 1, we put some rainfall in here, which was the same. Again, we were kind of using the data that we use for the New Orleans flooding problem that we got. And there's a very, very large rainfall of inches per day, actually. It creates a condition of flooding. And then we run for 3 months, for 100 days. And we just impose infiltration or evaporation. In this case, you can do a balance, right? You can do rainfall minus evaporation, and you can get kind of a infiltration balance, right, to that. And you can put runoff and everything in here. In this case, we said, okay, we're going to dump all this amount of water in a soil that is already at equilibrium with the environment. And basically what we're going to do is we're going to just impose some evaporation for 100 days. And you can put every day a different evaporation. You have weather station data, okay? Or you can put rainfall minus evaporation and get amount of infiltration or evaporation stage. So we impose an evaporation rate for every one of the sites that was basically found. That was actually this is the average annual evaporation rate for Louisiana, for Florida, for Texas, and for Arizona, right? So we got a lot of evaporation, like you can see in Arizona than Louisiana. And you're going to hear also about TMI. TMI is for Thorway Moisture Index. It's nothing but a measure of the balance between infiltration and evaporation, right? So this one will tell you the weather. Like I said, 20 plus 28 means it's a lot more rain. And now probably Louisiana is not that bad. Guwahati is about 50, 55. It's very high. -3 for Florida, -12 for Texas, and Arizona, -52. And we took some data based on different dates. But again, you can organize your condition as you please. And this is the pore pressure suction distribution that we found after we ran this thing. Let's say, for example, what happened in a very gravelly soil, and this is for the subgrade material, right? So this one is your steady state condition. That's when you started, okay? And then for day one, basically, you put all this water in there, and the suction goes immediately to zero, right? The water starts infiltrating until one point, and it goes like this. And then for day number 2, it starts recovering, right? It starts drying out again. So your suction is going to be greater, 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 until it gets into a more steady condition with the new evaporation rate that I put as a new steady state condition. If I run this one probably forever, right? You know, you're going to get into the steady state condition that you got initially, right? Same thing happening here with a soil like an L06 soils, which is a silty clay material. And basically you start with a condition, but day number 1, when you dump all this water in there, the suction reduced, but not that much as the one on that one, right? Soil is less permeable, so the water is not going to infiltrate. So what we happen is that always we think that soils that are very fine-grained material are going to be all the worst thing that we're going to have, right? Well, in this case, we're going to have more water in a sandy, gravelly material, obviously, right? So this is for day 1, and then it start infiltrating slowly, day 2, and then it start recovering as you go, right? So these are the suction. Notice something very interesting in here. If I had plotted water contents, and I got 3 layers in here, this is the granular base layer, this is the subbase layer, and that's the subgrade, right? If I had plotted moisture contents, probably you're going to have, let's say, low moisture, very low moisture contents, and then probably saturated for this one in here. But when you jump to the next layer, so you might have some water content in here, and then you jump to the next layer, you're going to have a moisture content in here, and you jump to the next layer, you're going to have a moisture content in here. It's not a continuity between moisture contents, right? Because you do have different materials. So they might be all saturated, and you're going to see the granular base is saturated at 15%, right? And the subgrade material might be saturated at 35%, right? So you do have same degree of saturation, but you do have different moisture contents. But what do you see here in the suction? Well, the interface between those 2 layers have to be at equilibrium. And the suction profiles should be a continuous function, okay? That's why it's the fundamental parameter that you need to check, because that's the reason, you know, is the only one that's going to give you that continuity on the functions that you get, okay? So that's interesting for you to realize in this one, if you have. So this is the pore pressure suction distribution. It's in my Yacine data. So I want to run a little. I had a little video here, so how do I run this thing? From here? It's nothing, I just show you with my, oh no, it is still on the writing thing. If you just click at the lower side, so how, just have to come back and just get out of, oh yeah, right there. I don't know if you can see that, thank you. Okay. So if you see this one is the initial, that's the next one, the next one, the next one. You see what, you know, I just, you know, I wanted to show you how this varies with until you get to 100 years, to 100 days in that case. Anyway, so that's for you to see the lines a little bit because we got a lot of lines in there. So this is the pore pressure, the suction distribution. Thank you. And these are the results of the suction distribution on that. Again, if you have day 1, and let's say we are in Louisiana, which is very, you know, wet, and for day 1, you have one of the soils that are very permeable. Check on the granular material and the subbase material. The thing is, this is too big, but if I wish I can do that. If you get into, I'm just trying to, doesn't work. Okay, I'm gonna try to show you. And in here, if you see the interface between those two, you're gonna see that the suction values in there are much higher than the suction values in here. That means that the water infiltrated all the soil in here because it was granular material, but in here, it infiltrated and almost saturated the granular base material, the subbase material, but the soil below is more impermeable. So the water basically were hanging out on these drain materials or very high materials, which is pretty bad, right? So the water did not infiltrate all the way down. So the resilient modulus in here might be lowering much more at the beginning than in here. In here, nothing happened to the subgrade. But the granular base material and the subbase material got totally inundated, okay? And then after 100 days, if you start just dissipating all this water, then basically you see that the suction just increase to a point when everything dries again, right? This one dries less because the water, just to take water out also it takes more time. Here. This is, we can do, that's what I was telling you about the degrees of saturation, right? For the granular base material, you may have different degrees of saturation. That for this, that's what I wanted to do. I don't know what I did, but that's what I wanted to do. Okay, and then in here, so now how I come back. All right, boom, boom, okay. So now we got suction values, all right? With the saltwater characteristic curve, we were able to get degrees of saturation, right? So we got all degrees of saturation. Now, how this is important to the practical engineering? So you did your work as a modeler, as a professional geotechnical engineering. You went to that point, and you go to the pavement engineering. Here are my results, right? These guys use this, or how do you guys, the pavement engineers in here, will use those results, right? So we do have a resilient modulus for the soil that is usually done in the laboratory at one water content condition. We do the resilient modulus at optimum, or we do the resilient modulus soaked, that we call soaked, which is the 100% saturated, and pretty much stop right there. You don't do more, okay? So you just do one value of the resilient modulus at one condition and use this value, and use this value for the design procedure forever, okay, for the 30 or 40 years of your pavement. Well, this is the value here. That's your initial value, all right? Now, because we were able to run a transient analysis and being able to incorporate, I'm done with this. I'm almost done, so I'm not that bad. Okay. We are going to use that value of the change in degree of saturation with time and figure out, or the change in degree of saturation with respect to the initial one that we got, the optimum condition. Usually granular base material are compacted at optimum condition, or plus or minus, so you got this value, okay? Or if not, you're gonna have to do some coring and figure out what is the density before the flooding to figure out what is your degree of saturation, something like that. But we do have a data before that, right? Which is this guy, the initial, and now you got, with the time, a change in degree of saturation. Well, we put together a model. This model is by Carlos Cari and me back in, 10 years ago, 12 years ago. And basically, we figured out for different soil types an environmental factor depending on the condition of your soil. When you have saturated condition, this is the optimum. Your degree of saturation at optimum are usually about 75, 85%, okay? That's your condition. After that, everything is almost, get all the way to saturation. The material type doesn't matter. You do have a saturated condition. There is not a big saltwater retention difference between that. But when you get into the drier condition and you get into soil that have a lot of clay, and WPI is nothing but the passing 200, the 75 micron passing value, multiplied by pi. That's how I relate the plasticity of the soil pretty much. Soil that are very high pi and WPI are clay materials. Some that are WPI equals 0, that is obviously non-plastic soils, right? So when you get into that, you can find that the factor of safety will increase about 2 times only for granular-based material, okay? When you have almost dry condition, let's say 75 minus 50, 25% degree of saturation. But when you get clays, you can get a factor, an environmental factor of 10 to 12 times. That means that your soil becomes like a rock. Have you seen a clay clot? You can break them with the fingers, right? And it's not because it has cohesion, because I don't believe in cohesion either, okay? It's because it has a lot of suction, okay? The water bridges holding those particles together, right? And you can break this suction with your fingers, all right? And that creates a factor of environmental factor that is much, much higher for those kind of materials. So you can do an environmental factor for every time step that you're using or you're looking at and figure out what is the change in resilient modulus with time, okay? And this one is a great way for them to take, analysis and take recommendations for whatever they want to do. So for that, we needed the resilient modulus at optimum condition, the degree of saturation at optimum. We found them for different soil types. Oh, here is the correlation between A1A is JW or JP, or A76 is CHCl or kind of stuff. So you got that in there. And these are the reduction in resilient modulus, the maximum reduction right below, like 0.2 meters below the sub-base material. And you can see that for A1A soil, there's reduction about 10, 15% maximum. But when you get into the A4, A6 soils, which are silty, clay, low plasticity, silty clays, you get a lot of reduction. You get into the 65, 70% reduction on resilient modulus, okay? And some of them will recover a little faster, right? It will recover faster in Arizona because you have more evaporation, right? Than in Louisiana when you have less evaporation rate, all right? So you can take decisions with this kind of data all the time. This one again, the resilient modulus, you can put the before and the after. This is the before value, and this one is going to be the after value. And this value they can use and figure out how much rotting they're going to have if they put this amount of traffic, how much permanent deformations or fatigue or all of that stuff, okay? And that's all I got for you. I hope you guys appreciate what, some CPH analysis. And it's not that difficult. It's just, to figure out a couple of properties, functions in there, and you can start running transient flow analysis. Have any questions? Sorry, I ran 7 minutes over your... Yes, sir?
Can you show the profile of such an isotone?
The suction profile?
Yes.
This one?
Yes. And
Yes, come in.
one is the initial.
This one is the initial. The initial is the steady state condition. Is gamma water times height from the groundwater table. So you got 0 value, and as you increase, right? Remember that this guy in here. Okay, I'm gonna show you the first thing. The first graph I show you. Okay, what is it? This one is this guy. Right there.
Negative pore water pressure, no?
Negative pore water pressure, right? Unsaturated condition. This is the groundwater table. I put it at 3 meters. And then you get all this. Like, the thing is, I did it on the other side, but it's the same, right? I did it with suction. So the negative pore water pressure is the same as suction. So that's your initial condition for that. And then you dump a lot of water. And what happened is this guy dumping a lot of water, this thing is going to go like this.
From negative, suction comes to the positive. No,
No, this
The
is
pore water
yeah,
pressure
the pore water pressure.
negative, and then
And less negative
positive or less negative.
will be less negative.
Ma-
But in the suction will be positive to more positive. Yeah. Yeah, so this one is in terms of pore water pressure, right?
Pore water
So
pressure,
that's what I put in negative. But this one is in terms of suction, right? This one is in terms of suction.
Ma'am, pore water pressure, no? Pore water pressure is negative initially.
Oh, okay. Well, I should have put, no, I should have put suction in here. Sorry. Here we go.
Yes, ma'am. So this one will be the initial suction, initial condition, no? That left one. Because pore water pressure is negative.
Well, I said that it shouldn't say pore water pressure, it should say suction profile.
So suction is negative.
No, suction is positive and is high positive. This one is minus 130,
This one is minus.
minus 130 pore water pressure.
Okay. If I consider.
So high suction is drier, right? This is drier.
If I consider that is the initial pore water pressure.
Exactly.
Okay.
No, yeah, this is the initial suction value. This is the initial suction.
Increases, when time increases.
When time equal 1, it goes
Yes,
down.
Okay.
And it gets to 0 suction.
At zero suction, but okay.
So 0 suction means saturated condition, right? Total saturated.
But at the bottom, ma'am, why this curve is
Well, because here is the groundwater table.
so?
So the groundwater table has some capillary going on in there, right? Still.
Ma'am, but the time before that, the graph is on right side. But
Well, yeah, the time before that, this is your pore water pressure. Oh, that's, you mean that why is a little
Yes.
bit in here? Well, it's because the water table, if the suction the water table probably went down a little bit or something. This one is 0, 0. You see that? So if you got a little bit in here, is that the model was not able to get one in
exactly
here.
why it is on right
Don't
side.
get into little things. Doesn't matter. It doesn't matter, but you're right. Okay, so in here, there is a little bit of change in suction from 0 to 5 kilopascals. That means that it gets a little bit drier than it was before. So it means that the water table went kind of a little bit down, right? But this is all on the morally boundary condition that you have to accommodate probably to get the numbers, right? But this one is essentially 0 all the time,
Yes, ma'am.
like this one. Yeah, exactly. You're right. Thank you so much. Any other questions? Yeah, there are
Hello, ma'am.
modeling situation that you got. You're gonna consider that the model is gonna be doing something not to fail, right? Not to crash, and this is probably one of them. Yes. Yeah. Raul?
Yes. If we simulate this condition during the rainy season and we want to evaluate over 90 days, and what is the right time to quantify equilibrium moisture content along the season?
Well, if you have, this is your time, right? And what you're saying in here is this is rainfall, right?
Yeah.
And probably some evaporation in here, right? So you do have some rain, a little bit of rain. And also you can have some evaporation in here because you are in a certain place when some evaporation occurs, okay? So what you're gonna have for every day is a balance between rainfall and evaporation, right? So which one do you consider to be an equilibrium value?
Yeah. No, at the end of the season, is it no?
I believe that if you want to design for something, you're going to design for the worst condition. That might be, okay, I have a lot of rainfall in here, so I do have my resilient modulus going down. But you're right, if you check that one, it said, okay, my resilient modulus start right here and get a lot of, So in here and then go down because of the rain, right? Start going down, and some high in here and then going more down. So you're going to have this in here. Eventually, if you are designing a road for 30 years, ideally what you want to do is to figure out what is the average value that's going to happen. But if you want to include a little bit, this one is prone to flooding conditions, you're probably going to be adding a percentage in here or a percentage down here and design for a value in here. But this one might be even higher than the optimum or sub condition that you're always designing for.
Mhm.
And you are saving that money in the, I'm telling you, 1 centimeter, 1 inch of asphalt is millions and millions of dollars.
Yeah.
Okay, and that's the only difference, your resilient modules.
And the software, does it allow us to place a wheel load at the top and see what is the deformation we get at the top of subgrade or something?
You're talking about software like MEPDG, like
Yeah. No, in this Plexus Studio.
in this one, yeah, you can.
We can.
You can put, well, still consider the overburden pressure because I put the densities of the asphalt, granular base material, and all of that, right?
Huh.
So I did that. So it will consider that. But if you put any more load, yeah, but it is considering the overload.
Okay.
Now, what it's not considering is the resilient modulus changes due to the traffic load. There is no Hyversine load that you put in here. But supposedly, and you're going to see that, I'm just kidding. Okay, here we go. When you use this equation, actually the resilient modulus, that's going to be in the next lecture, right? I'm going to teach you how to get that value. And that is a function of your traffic load. So here is your traffic external load, and this one is your environmental load. You have the two loads. The problem is that, it's an uncoupled solution, but it's a solution that is easy to implement for practitioners, okay? That are more complicated that you're gonna see that in a minute. All right, let's take some tea time, and let's come back in 20 minutes, right? Great questions in here. Thank you so much.